So here in this example, we are given, again, AB and BC, two cylindrical rods connected together. We're given the area of AB, area of BC, and modulus of elasticity. We have a 10 kip load applied along the axis of ABC at point B, and we are asked to find the wall reaction, the displacement at B, the internal forces in AB and BC, using the finite element method. So we're going to go through the steps, and the first thing I want to do here is to identify an element that we're going to be used. And looking at this problem, we see that AB and BC are going to behave like bars, either in tension or in compression. And we've already checked whether C is going to hit the wall or not, and we learned that C is going to hit the wall. So from that, we learn that the displacement at C in the x direction is going to be equal to that clearance of 0.002 inches. Another boundary condition we see here, because the wall is fixed at A, is that UA is equal to 0 inches. So these are the two boundary conditions looking at the problem here. So first thing I want to do is to select an element and discretize. So I'm going to come here, and next to that, I'm going to say on my first step, step number 1, select a bar element and create a mesh. So I'm going to do my mesh. I have a bar AB and another bar BC. So here I have A, B, and C. AB and BC share the node B. Everything here is oriented along the x-axis. At B, I do have a force applied, external force, of 10 kip. And at A, I do have a support reaction that we are yet to find. And I'm going to show it here in the negative x direction. I'm going to call it RA. And at C, I also have a wall reaction RC in the negative x direction. The length of AB is 10 inches, and the length of BC is 12 inches. So this is here my mesh showing the loads, and we already have described the constraints UA and UC as we have the two walls. So UA is equal to 0 and UC is 0.002 inches. Next, I'm going to write the element stiffness matrices. So in step number 2, I'm going to write element stiffness matrices. And for a bar element, K is equal to EA over L multiplied by a 1, a minus 1, a minus 1, and a 1. So we have a 2 by 2 matrix. I'm going to label my elements. So if I label this as element 1, AB, and label BC as element 2, element 1 is going to extend between the nodes A and B. I'm going to number them. So I'm going to call this node 1, this is node 2, and this is node 3. So the stiffness matrix for element 1 is equal to EA over L, where I have 10 times 10 to the power 6, multiplied by the area, which is 1, divided by the length, which is 10, multiplied by a 1, a minus 1, a minus 1, and a 1. This is equal to 10 to the power 6 times a 1, a minus 1, a minus 1, and a 1. Likewise, for element 2, we're going to have a K2, and this is equal to 10 times 10 to the power 6 multiplied by 1.5 divided by 12 times a 1, a minus 1, a minus 1, and a 1. And this is equal to 10 to the power 6 multiplied by a 1.25, a minus 1.25, a minus 1.25, and a 1.25. While we're at it, I'm going to label rows and column based on corresponding degrees of freedom. So element 1 extends between nodes 1 and 2. So I'm going to come here and label the first row as 1 and the second row as 2, first column as 1 and second column as 2. For the second element, element 2 extends between nodes 2 and 3. So the first row, I'm going to label it 2, second row is 3, first column is 2, and second column is 3. Next, I'm going to go to step number 3. Where I'm going to assemble the stiffness matrix K using the direct stiffness method. Where K is equal to the sum from I equal 1 to 2 of the element stiffness matrices. And knowing that this has 3 degrees of freedom, we expect this uppercase K to be a 3 by 3. Looking at K1 and K2, we see the 10 to the power 6 as a common factor. So I'm going to take 10 to the power 6 as a common factor. And I'm going to be superimposing the entries here corresponding to the rows and columns number. So I'm going to label 1, 2, and 3, 1, 2, and 3 for rows and columns. And I'm going to start with element 1. So I'm going to have here a 1. I'm going to have here a minus 1. I'm going to have a minus 1 and a 1. So this matrix here, or these entries, are coming from here. Next, I'm going to superimpose the stiffness matrix for element 2. So I'm going to come here and look at my first entry. I have a plus 1.25, row 2, column 2. So I'm going to come here and put a plus 1.25. And here I have a minus 1.25. Here I have a minus 1.25. And here I have a plus 1.25. So these elements here from the second matrix came here. For all the cells that do not have entries, we're simply going to put zeros. And I have 2 of them. So now if I break this here into show like a grid so you can see where every entry belongs. We can write this K, the 3 by 3, as equal to 10 to the power 6, multiplied by a 1, a minus 1, a 0, a minus 1, a 2.25, a minus 1.25, a 0, a minus 1.25, and a 1.25. Next, step number 4. We are going to write the global stiffness equations. Namely, F is equal to this uppercase K and its uppercase F multiplied by U. So for F, we have the external force at 1, which is a minus RA. External force at node 2, which is 10,000 positive. And the external force at C, which is a minus RC. Oops. This is equal to K, which is 10 to the power 6, multiply by 1 minus 1, 0, minus 1, 2.25, minus 1.25 is 0, a minus 1.25, and a plus 1.25. Multiply by the nodal displacements, U1, U2, and U3. So these are the three global stiffness equations. And I want you to notice that the stiffness matrix is a square symmetric matrix about the major diagonal. The major diagonal is all positive. And you can see here the symmetry, a minus 1, a minus 1, 0, 0, minus 1.25, minus 1.25. This stiffness matrix is also a singular matrix, meaning there is no inverse for that. You cannot find an inverse for this matrix. So in order to solve the global stiffness equations, we need to apply boundary conditions. Okay? And this would be step number 5. So in step number 5 here, apply the boundary conditions, namely U1 equal to 0 and U3 equals to 0.002 inches. So I'm going to have an RA, a 10,000, a minus RC equal to 10 to the power 6 multiplied by a 1, a minus 1 is 0, a minus 1 is 2.25, a minus 1.25 is 0, minus 1.25 and 1.25. Multiply by U1 is a 0, U2 is unknown, and U3 is a 0.002.
Is RA negative or positive? Because it shows
Negative, I'm sorry.
Okay.
Thank you. So now when we look at this carefully, we have 3 equations and 3 unknowns, namely RA, RC, and U2. Since U1 is a 0, I can start by omitting the first row or the first equation, and everything in the first column is multiplied by 0. So I may choose temporarily to just omit the first row and the first column. And now we are dealing with 2 equations. So now I'm going to be solving or unknown displacements. So I have this 10,000 is equal to 10 to the power 6 multiplied by 2.25 U2 minus 1.25 times 0.002. This is the second equation, among these three, and we can solve for U2, and we find that U2 is equal to 0.0055556 inches. And U2 is the displacement of B. So this is one of the required solutions. Once I have U2, I can solve for RC. And here we have minus RC is equal to 10 to the power 6 times minus 1.25 multiplied by U2, which we just solved for, plus 1.25 times 0.002. From this, we find that RC is equal to 4,444.4 pounds. So I would add here that we're solving for unknown displacements and forces. Okay. I can use equation 1 to solve for RA. So RA is equal to a 10 to the power 6 multiplied by a minus 1 times U2, which is 0.0055556, plus a 0 times 0.002. From this, we find that RA is equal to 5,555.56 pounds. And finally, on step number 7 here, we're going to use element stiffness equations to find the element forces or the internal forces. In each element. So I'm going to start with AB, or element 1. And remember, the element stiffness equations are F equals to the K, and these are lower cases, multiplied by U. So if I sketch the element, if this is element 1, I'm going to have an element force F11 at node 1, and at node 2, I'm going to have another element force F2 for element 1. So when I expand element stiffness equation, I'm going to have F11, and here I'm going to have F12. These are equal to 10 to the power 6 multiplied by a 1, a minus 1, a minus 1, and a 1. And the displacements at nodes 1 and 2, at node 1 is a 0, and at node 2 we found that this is 0.0055556. So when I do the math here, I'm going to get a minus 5,555.56 or 0.6. And here I'm going to get a plus 5,555.6. So what is that telling me? It looks like one is positive and one is negative. But if I look at the drawing I'm showing here, showing the forces along the positive x direction, it's showing that F11 is negative, meaning it's going from the right to the left. And at 2 is going from the left to the right. So element 1 must be in tension. So we can conclude from that the normal force in AB is 5,555.6 pounds in tension. Next, if we look at BC or element 2, and if I sketch element 2, extending between nodes 2 and 3, corresponding to B and C. If this is the positive x direction, I'm going to show my element forces going in the positive x direction as F22, because this is element 2, and F23. I'm going to write the element stiffness equations. F22 and F32. Oops, I wrote this here wrong. Sorry, this is 32, not 23. Applied on node 3, element 2. Okay. These are equal to 10 times 10 to the power 6 multiplied by 1.25 minus 1.25 minus 1.25 and 1.25 multiplied by displacement at 2 is 0.0055556 and displacement at 3 is 0.002. This is equal to 4,444.4 and a minus 4,444.4. Now look at this. This time, the node to the start node or node 2 has a positive, meaning that this F22 is going from left to right or pushing on 2. And if you look at node 3, this is negative. So this is also pushing at 3. From this, we conclude that BC or element 2 is in compression. And I have a normal force NBC that is equal to minus 4,444.4 pounds. Or NBC is in compression, right? So I can say this is as negative sign, or I can write it that NBC has 4,444.4 pounds in compression. Same thing, negative sign or compression means the same thing. So with this, we were able to apply the stiffness method to solve the same example we were able to solve using the classical method.